Hey people, Wall here with Wallcraft, and today we're going to be doing a brief tutorial on how to fix some of the problems that arise when converting assets from later expansions down to vanilla. And particularly we're going to be discussing wheel animations and the funky behavior that you'll see when converting assets from Lich King or higher down to vanilla concerning wheels. So let's get right into it. Uh, for those of you who are familiar with the conversion process and have used assets in the vanilla client from later expansions after having converted them with JM2, you'll probably have noticed that there's some issues with wheels. Any object that has a spinning animation on one of the bones, you'll notice that here, we'll play it for you so you can see. You'll notice that the wheel has this problem where it resizes as it's spinning. It'll shrink and it'll grow. That's an issue associated with the converter, and it's unfortunate because I don't foresee a fix for the converter happening anytime soon. So, it is what it is, I guess. But there is a solution. There is a fix. If you're willing to dig through the model itself, you can fix this. We're going to play it again so you can see the resizing that happens. So, the fix and the problem, we're going to discuss that in depth and show the solution. First off, what we need to do is get the model loaded into 010 editor. And you can see that I have the file open right now. This is motorcycle fell reaver mount.m2. I'm not entirely sure which expansion this is from. This was sent to me by somebody to take a look at and try and fix. So we are able to do that. We're going to make a tutorial now detailing that. So first thing we need to do, of course, is get our M2 template. This is the Alistair M2 template. It's not the most recent version. It's a few months old. I should update it, but plenty fine as long as you have the Alistair M2 template with the latest basics.h header file for it. We just load the file for the M2 into 010, and then we open template. And this is the template that we have opened, and we're going to select the asset and run the template. If you've never used 010 before, it's pretty complex, so you might want to take a look at some tutorials first, but essentially what we have is the entire file open in a hex editor here, a binary editor. So we're looking at the file, and the file is in a chunked file format, and it has different sections to it. I'm not going to do a full 010 tutorial. I'm going to assume that you have basic understanding of it, but we'll talk about some of the basics here that we're looking for. In the file, when you have it loaded in the template, run on it, you'll see all of the details for the file. The template basically parses the file and shows all of the data in these little sections here. So what we're looking at right now for this entire section all the way down to here is the header, and this will show where all the offsets are for these various sections below. So the problem that we're looking at, of course, in this video, play it again, is the wheel itself has its freeze frame. The wheel itself for the front wheel is a separate bone that it's attached to, and when you convert from Wrath of the Lich King or higher down to vanilla, the format for the quaternions and the timestamps is entirely different, and the converter does not handle it well, unfortunately. There's some issues with the converter there, so Wrath of the Lich King uses C4 compact quaternions that are stored in, if I recall, unsigned 16, whereas vanilla uses full uncompacted quaternions that are stored in floats, or read as floats. So when we're looking at this, you'll notice that there's going to be a radical difference in the pre-converted portion for the quaternions that we're looking at and the vanilla version. Uh, so the first thing that we need to do, we need to identify which bone is being used for this wheel. And often you'll see the key bones are labeled. When you go into bones right here, you'll see that the key bones are labeled, such as wheel 2, wheel 1. You would assume that that's the bone that's for the wheel, but not necessarily. That's the key bone, but that's not the bone that's performing the rotation here. So for the front wheel, wheel 1 on this model, the front wheel would actually be bone 13 here. And you can see in bone 13 it has an M2 track for rotation, and that rotation has 66 timestamps and 66 keyframes. We're going to expand this out further, and when looking through the rotation, you'll see it has interpolation ranges that are used at specific timestamps. It'll have timestamps pairs and the list of the timestamps, which is just a raw list of timestamps here, and the values for the actual rotation. And these are the quaternions that we're referring to. As I said, vanilla uses uncompacted floats to store the values, whereas Wrath of the Lich King uses only 2 bytes there. And when we're looking for the rotation, we're looking for it in a specific bone. We need to find out which sequence is associated to that, along with the timestamps that are used on the sequence. So here, let's go back here. We've got the sequences structure. We're going to expand the sequences structure, and we can see the list of animations here. So for this vehicle, the problem is when the vehicle is moving, the bone is spinning, and the quaternions are fucked up. So the rotation is causing the model, the bone portion here, to shrink and expand. And you can see it in the video. It'll shrink and expand and shrink and expand. And that's because, again, the converter messes up the timestamps, and it also, I don't know if it's throwing, I don't think it's junk data, but it's not written correctly, not fully correctly. So, you know, there's just some problems there that we're going to fix manually here. First thing we're going to do is we're going to look at the 3 sequences that we're going to be needing to modify. And that would be walk, walk backwards, and sprint. Not run. Run is a different sequence. In fact, I might need to fix run, I'm not entirely sure, but sprint is what's used for full speed mounts. So walk, walk backwards, and sprint. We're going to take a look at walk first and see the start and end timestamps. Now, these were already changed in this model, but the previous version had different values for that start and end timestamps, and those don't actually align to all of the animations, so it causes issues where the timestamps are between 2 different quaternion sequences, and that's what causes the bizarre shrinking and growing lerping effect, as it's blending between the 2, and one of them isn't actually a valid part of it. So it's blending from different portions of the animation. So what we did for this was we looked at the timestamps, the start and end timestamps. They weren't correct, but we can go down to the bones timestamps and we can find out which one is closest to it. The previous value I think was 310 like 55 or something on the original model. So obviously the closest one to it is only like 40 frames off. And that's something that you'll notice commonly, is that it's only a few frames off. Your 2 options essentially are changing the sequence timestamps or changing the timestamps directly in the bone. I would recommend changing the timestamps directly in the bone, because that sequence timestamp, even if it might not be correct for that current bone that you're looking at, it's probably correct for a different bone that you're looking at. So just by changing the timestamps that are used in the sequence, we can more effectively handle that. Now you can see the sequence 31099 on the timestamp, and 31566 is what's used for the walk animation. That is timestamp 8 and timestamp 9. There is a timestamp pair for every keyframe value, for every quaternion. So for 8 and 9, what we need to do is lerp between two positions. We're going to look at that again real quick. 31099, 31566. Again, we're going to look at the timestamps 8 and 9. So then we go down to the quaternions 8 and 9, and these have values. These don't necessarily need to be modified, and if you do have to modify them, good luck, because they're quaternions. They're not meant to be modified by humans, basically. So what we did was adjust the timestamps to use the correct range of values. And you can see that the neutral default position on the quaternion is typically labeled 0, 0, 0, and then 1 for the W scalar, so 0x, 0y, 0z. Now 1 for the scalar, that means it's in its default position, so what you see when the model is, not animated, standing still. And then we're going to lerp to this value in quaternion 9. Now this is where I'm talking about the junk data that's being written by the converter, because this is definitely not Blizz-like. You wouldn't see this in a Blizz-like model. This should really be 0, but it's at a minute fraction to the point where the template doesn't even display it properly. So if you see something like this, it's probably junk data in some sense, but it's also not. It's accurate to a degree. And it's just because the conversion process between compressed and uncompressed, or quaternions, packed or unpacked, I should say, compacted. But we're going to ignore the actual quaternion values right now, because for this one we have the values in this sequence. The timestamps were just screwed up. So we changed the timestamps. Go back down. We changed the timestamps to match between these two values, and the wheel is able to effectively lerp between the two. And again, for this model, I changed the sequence timestamps for them, but I also changed for other things the bone timestamps. So walk, run. We're going to go down to the next animation here. Or I'm sorry, not run. Run isn't used. Walk backwards. So walk backwards, and sprint. Walk backwards is the next. You're going to see a different range of timestamp values, 41765, 42232. They go back down to the front wheel bone, and we look at the timestamps, 41765, 42232. Now, typically in these wheel animations, it would be a stretch of timestamps. It would be like 5 or 6, typically, and the wheel is handled in these segments. So if you think about like a circular wheel and it's turning like a clock, you can divide it up easily into quarters or even eighths or whatever fraction you really want to use. And you can have timestamps for each of those positions, and the renderer will lerp between those values. So imagine like an hour hand on a clock, how it moves smoothly, but kind of in reality it's not moving smoothly. It's moving at at a relatively set pace for each quadrant that it's moving through. It's more akin to like a second hand that is moving smoothly, or moving at a jarring rate. But the renderer will blend between those sequences smoothly, so you don't need to include every single individual degree of rotation. You just include 4 typically at the minimum. But the thing is, with wheels, especially wheels that are moving fast, you don't actually need them. You can use just a single timestamp, and imagine the wheel is turning 1/8. Well, instead of lerping to next position, we just snap back to the original one instantly and then make that 1/8 rotation. And since it's a wheel with perfect symmetry, the user doesn't really notice it. If the animation blending isn't done super well, based on the quaternion values, it might look kind of shit, but not particularly, especially when it's moving very quickly, you don't even notice it. And we'll show you the model after we've done with this. So instead of using, like I said, instead of using a range of timestamps to do this, we can just use 2 different values of timestamps and then achieve kind of like that fan effect where if you look at like a wheel or a fan, a ceiling fan, it'll look like it's spinning backwards after you stare at it for a while, but it's actually not, you know. Achieving the same kind of visual deception with the rendering magic. So we got 41765 42232. This is the walk backwards animation. And we're going to look at the timestamps that are used, 18 and 19. Go down to the quaternions, 18 and 19, and we can see that it's lerping between the 2 same values as the previous one. Now, for a walk backwards animation, I need to actually fix this on the model because when you walk backwards, the wheels still play forward. Typically, there's a flag that you can use to set backwards animation, but I tried it and it doesn't really seem to work in this case. There's probably a need for a range of timestamps and it needs to fully cycle it. I'm assuming it assumes end position is the default. I checked other animations for wheels and they just use like an actual quaternion value for backwards rotation. This is just the forwards one, so I do need to change this to, you know, make the wheel spin backwards when you're walking backwards. But, you know, for the example, it's fine. I'm not going to mess with that right now. But you can see it's lerping between the 2 same values as the previous one, 8 and 9. So it's the same animation. We're going to look at the last one, of course, which is Sprint. Sprint 47098, 47565. 47098, 47565, 23 and 24. So we go down to the 23rd and 24 rotation, and you can see it's, again, the exact same as the previous 2 sequences. So the walk forward and the sprint, which is the fast walk forward, you know, typical riding speed animation, and as well the walk backwards, all have the same animations here. And again, the walk backwards should have a reversed animation, but that's fine for now. So they all have the same quaternion values, and they lerp at the same rate, which is what is desired for a wheel. By fixing these timestamp values, we're able to effectively adjust how it's handled, and then, again, with the quaternions, they're lerping between these values. These aren't really meant to be edited by people. They're meant to be edited by computers. Like when you're using Blender and you're creating an animation, you're not punching in numbers. You're just adjusting the model, and the computer handles all the math for you. So doing this by hand is pretty difficult, but there is some cheap tricks. What we're going to look at right now is we just finished looking at the front wheel. We're going to look at the back wheel now, because the back wheel of this model that was sent to me didn't work. It wasn't implemented. All that was a quarter rotation animation, but I was able to use the previously described trick to implement the full rotation by using the same, you know, rendering deception magic there. So let's take a look at the bone for the rear wheel, which I believe was 11, if I recall. Let me take a look, make sure. No, it's not 11. It's tricky to figure out which exact bone is used for the exact animation because it's not actually labeled. Like I said, the key bones that are labeled aren't actually the ones that are used for the animation of that bone. Usually you can find it by following the chain down. So bone 12 has a parent of 11, which means it's attached to bone 11. Bone 11 is attached to 7. 7, I believe, was actually it, yes. 7 was the correct one. So going down the chain, the way that I find it is I just go down the chain, and for each bone, I'll start at the key bone. I'll go in and I'll just zero out all the timestamps. And then if the animation stops, that means I found the right bone. And then I, undo it also. The timestamps are fixed. But I'll break the timestamps so that the bones shouldn't have animation then. And then if the animation does break, it means I've found the correct bone. So we go to bone number 7, which contained the animation for the rear wheel. And for this, because the rear wheel wasn't fully animated, we had to actually add the quaternions ourselves. Actually, no. Was it 7? I don't think it was 7. No, I'm on the wrong bone. Which one was it? Not that. Oh, dang. Which one was I working on? Now I can't actually remember. Now I gotta find it. I'll be able to tell which one I was working on by looking for the values, because I used fake values. Yeah, go digging through the bones here. Wheel 2, parent bone is 6. Was it 6? It might have been 6. Let's see. Okay, yeah, it was 6. I can tell because I had to simulate quaternion values. Again, you're not really meant to be able to do this. Just how quaternions work. Creating values out of thin air is not really possible for anything complex except partial rotation. And that is because we don't have to perform a full rotation. All we have to do is perform a partial rotation, and that is relatively simple, provided we're on the correct axis. Such as modifying the x value would cause the wheel to not turn sideways, but turn diagonally. And trying to make it turn diagonally or sideways is even more of a pain with quaternions. But luckily, forward rotation or wheel spinning rotation is typically associated with the y-axis and the scalar, the W. So for this bone, the rear wheel of this vehicle, we need to find, of course, the timestamps. And for this one, I changed the timestamps in the bone to match. So we can see, we go to the timestamp list of bone, and let's go back and look at the sequences and what timestamps they use. So sprint 47098, 47565. We go down into the bone, and we see 47098. This value was changed to match the timestamp of the sequence. You just look for the closest one, because really these timestamps are just associated to the quaternion. They're basically a list of timestamps that the animation plays through. It selects and then plays through the animation between the two or more ranges of the timestamps here. And the time itself is effectively just to determine how fast the animation moves. But the actual position is stored in the quaternion here in the rotation, or in the translation, which is a C3 vector, or scaling, the C3 vector scaling. So back to it though, 47098 and 47565 is quaternion 55 and 56 for the rotation. And you can see the faked values that we have. We do a quarter rotation with value of, or I'm sorry, 3/4 rotation, and a value of, I'm sorry, I misspoke again. Not 3/4 rotation, it is a quarter rotation, because even though it's 0.75, it's only moving 25%. And then, of course, a quarter on the scalar there. And it lerps back to a full position on the Y, and 0.25, so 3/4 basically on the scaler. The math is a nightmare. Don't even worry about the math. Again, if we're just doing basic rotations, we can use these values, 0.75, 0.75, and then 1 and 2.5, and that'll get you where you need to go. A little bit of a math hack for that. So we have those values assigned, and then that's basically it. We have the values assigned, the timestamps are correct, and we have lerping between these happening endlessly. So we saw the problem originally, and let me pull up the video here. Let me find the video that I just sent. Look at that. And then this is the fixed version. So you can't even notice a problem there. The vehicle itself kind of jumps up and down, bounces as it's moving, so that's just all you're seeing there. But yeah, you can see a few clips here. I fixed even the jump land animation, which is a problem that does affect higher version models, which I'm willing to cover real quick here. Moving on to the next topic here, just briefly, is the jump land animation, or any animations, basically. You'll notice when you convert a mount, typically, from a later expansion, especially like Legion or so, down to vanilla or pre-Wrath, it will have problems when the animation is supposed to cycle to a different animation after it's finished. One clear example is jump, land, and run. Jump, land, and run is what happens when you're on a mount and you're running, and you jump, and then you land, and you run, and you're still running. The mount has to perform the jump start, the jump animation, the jump land animation, and it has to reset back to the running animation that you were using. So it's a pretty complex chain, and unfortunately the converter seems to mess this up. I think it's because, and again, I'm not super savvy on later expansion M2s, but I believe that they just use a different method of handling the animation cycling. I believe it's, handled somewhere else. But for the vanilla conversion, you need to look in the sequence fallback. Wrath of the Lich King converted models, like this one, this is, yes, it's a later expansion, but it was converted to Wrath of the Lich King to be edited in Blender. So it's a Wrath of the Lich King model in essence at that point, converted for vanilla. So the sequence fallback is what's used to determine which animation should play next. And the way that we find that is by looking at the global list of animations. You can find this in the client, the animation data, DBC. Or you can alternately just look on WoW Dev. We're going to pull it up in the DBC though. Animation data. And what we're looking for is jump, land, and run. So jump, land, and run. Scroll down. We can use the search feature, but I know it's 187. So 187 is jump, land, and run. We need to find this number here to reference it in the sequence fallback. And it's because the sequence fallback is just the same list contained in the model. So we go to 187, and originally this was fallback animation ID was also 187. You'll notice that most of them are blank unless they either have their own ID or a totally separate ID. 158 is an example of the fallback having its own separate ID, which I don't even know what 158 is. Hold. Yeah, so that should just hold. So when you do like a hold animation, which would be like when you open a chest and you're holding as you're like kneeling down, kind of whatever, something similar like that. So for like the hold animation, you want it to just hold itself. It'll fall back to itself once it ends, and it'll just hold that position. Jump, land, and run obviously shouldn't do that. You need it to cycle to the next animation of running, or I should say sprinting would be the animation that's used. So we want it to cycle to sprint. Sprint is 143, and that's what we changed in there. Oops. So that's what we changed in there. We set the jump, land, and run fallback animation ID to 143. And you can see that in the video. I don't know if I jump in this. Yeah, so you can see when I perform the jump, I land and it just continues cycling the animation. Previously, it would jump, land, and then the animation would stop and the vehicle would just be sliding along on the ground at that point until you started a new animation by manually stopping and starting again. So that was able to be fixed. Um, Really, the only thing left to do on this model would be implement walk backwards for the Quaternions, but I'd have to basically brute force Quaternion values again, so is what it is for now. If person who sent me this model, if they want to try and mess around with it, they can. Not a problem there. Yeah, anyways, so that's it. That's how you fix the choppy wheel animations that result from down converting. I hope this was informative. I know it was a bit of a ramble, and it's a really niche subject that not many people will actually use, but for those out there that will, good luck. You're going to need it.